Our speaker is Justin Linkachong. He's a research assistant, plastics engineering from University of Massachusetts. He received his Bachelor of Science degree in plastics engineering from the University of Philippines in Diliman, and I believe he completed that in 2016. Justin's going to talk today about the determination of physical properties of fused filament fabrication parts as influenced by the nozzle. And Justin, are you there?
Hi, Mr. Spalding. Yep.
Justin, the podium is.
Thank you. So, good morning, everyone. My name is Justin Linkachong, and today I'll be presenting research that me and my colleagues from the University of Massachusetts Lowell conducted last year with our Professor David Kazmer, who also did a talk on additive manufacturing and extrusion last week. So our research was entitled Determination of Physical Properties of Fused Filament Fabrication Parts as Influenced by Your Nozzle Diameter, Road Height, and Shear Rate. So just to give you guys a quick background on my research, the research what we did, according to Redwood, Scofer, and Garrett in their 3D book hand printing guide design, your resolution basically is affected by your layer width and your layer height. And your layer width is basically a function of your nozzle diameter, which you can vary from around 0.25, 0.4, and 0.8 millimeters, which we did. I know that you can also go up high as like 1 millimeter. Meanwhile, your layer height, which is your distance between your nozzle and your printer bed. And as you can see in the graph here, depending on how close or how too high, that can affect basically your bed adhesion, or your print adhesion. So going too close can give you thin and excess layers, while going too high can give you this bleeding effect and give you poor adhesion. So something that we did in this research that was quite different from other people was that we saw how our filament varied our parts, or basically how filament variations affected your printed parts. So again, our main motivations were, again, aside from resolution, we wanted to see how this propagation of variance, as they called it, affected your initial parts. And so what we did was we created our own filament, then we characterized it using a laser micrometer, which I'll show you in the next few slides. Then we did a design of experiments, and we 3D printed it and basically varied the different process settings to find the most robust process settings. Finally, we tensile tested and did some statistical analysis in R. So we used polylactic acid, which is one of the more common fused filament fabrication filaments that you can find in the market. Then we extruded it using a single screw Davis standard extruder at UMass Lowell. Then we used a laser micrometer to find its diameter. Then we printed it using Ultimaker 3, one of the more higher end or pricier fused filament fabrication parts per se right now. So here's a quick, basically a video or GIF of the whole process of creating that filament. So as you can see at the beginning, you'd see that Davis standard single screw extruder. So it passes through a water bath, which basically cools your filament. And then through the laser micrometer and data acquisition system, which we hooked up in the belt board. So these are the different processing parameters that we used in order to create that filament. We basically follow the standard basically made by NatureWorks in order to create the 3D printer filament. We dried it for 4 hours at 80 degrees Celsius, and we wanted to create 2.85 millimeter diameter filament, which was required by the Ultimaker 3. From what you guys know, you also have 1.75 millimeters, which is more commonly used. In terms of our 3D printing settings, we did an infill density of 100%, an infill pattern, cross infill pattern, and we printed it around 205 degrees with a bed temperature of 65. In order to compare apples to apples for our different DOE runs, we ensured that we had the same volumetric output of 1.6 millimeters cube per second, and we printed basically ASTM tensile type 4 bars. So something I wanted to point out here was that according to Cura, our slicer software, our parts should have weighed around 8 grams and used 1 millimeter of filament. So here is the data that we got in terms of our cross-sectional area of our filament. As you can see, our filament is quite bad per se. So again, we wanted to make 2.85 millimeters, which gives you a cross section of around 6.38 millimeters per squared. And that gives you around an error of 2%. In comparison to commercial filament that we also bought, that we just wanted to compare, our bought polycarbonate filament was only around 1%. So you could clearly see that our filament was somewhat inferior, because I know, again, once you do with 1.75 millimeter filament, their tolerances are only around 1 plus minus 0.05 millimeters. So as you can see on the lower right-hand side of our presentation, typically you want to have a spherical or a good, that's a good example of a good filament once you cut it down in its cross section, while our filament was typically more ovular, or again, it was bad filament. So here is a summary of our design of experiments. As you can see, we varied our nozzle or road width and road height. So typically you want to have your road height set around 80% or below 80%. There's some type of optimal thing. There's our optimal basically range of it. So that's what we try to do. In terms of the nozzles that we used, you can see that we used a 0.25 and 0.4 and 0.8. We also converted our speed or lateral velocity to our shear rate, which is basically your velocity over your road width. And something that I wanted to point out here too again was that we actually omitted our runs DNA, which were highlighted in red, because we didn't set our nozzle and road width equal. You can see that it was set to 0.25 and not to 0.25, which we corrected in runs G and H. However, we thought that there was still valuable information that we wanted to present, or the different images, which you'll see in the next few slides. So again, we also show that the different dimensions that we have for our FDM tensile type 4 test 4. So here are some representative samples that we got, that we printed. And as you can see that in terms of our smaller nozzles, which you can see as runs A, F, G, and H, you do see very good resolution. But if I had to give it to you right now, it's a bit of a flimsy port in comparison to the higher nozzles at 0.4 millimeters. The printed samples that we printed at the larger nozzles at 0.4 millimeters and 0.8 millimeters. At the highest ones at 0.8 millimeters, you can see that you can actually see through it, but again, it's very stiff, and you can actually see this relationship later on in your data. Another thing I wanted to say was for runs G, you can see that there was some problems in adhesion that we also experienced in our 0.25 millimeters, so it's quite hard to print these ones. And again, you could think of it as maybe we had some filament slippage or different, again, process parameters, things that you might have overlooked. So here's the tensile videos that we did. So you typically see a brittle failure in our 0.4 and 0.8 millimeter nozzle diameters, while you see this interesting fiber-like breakage in our smaller nozzle diameters at 0.25. So it's quite interesting where it's like at some points, it's basically just printing one line of layer filament once you pull it at a certain length. So here are the different sample failure modes that we got. Again, we see a brittle failure in the higher or the larger nozzles, and more of a fibrillar breakage in the smaller nozzles. Something again that we had a lot of problems for the A's and D's for the smaller nozzles, but again, you can see it's very flimsy, and you can still see some value, and that's why we presented this data here. So in total, we tested around 146 samples. And it took around 1 hour for each sample. So that was a lot of work. We printed around 15 samples, except for the runs, the smaller nozzles, where we printed a little bit more to further test whether it was really just a printer or we had different problems with it. And so again, we ensured that all of these values equal to a volumetric output of around 1.6 millimeters cubed per second. So here are some stress and strain curves that we generated through MATLAB. So we didn't use the Instron outputted stress and strain curves in order to offset, because once you initially pull it, there is some, basically we wanted to offset that error. And as you can see for our larger nozzles at runs B, C, and F, you see that again, this is all scaled to 40 megapascals. You see that you see that brittle failure, and again, you see that it's quite good. It's interesting to see that in runs G and H, which were smaller nozzles, you do see a longer strain, but again, at this point, you know, basically it's already beyond the plastic region. It was already broken. Moreover, in terms of E, which I'll show in the next slide, it was interesting to see that it significantly had lower tensile strength versus the other nozzle diameters of its 0.4 and 0.2. And we can kind of see this because of that layer for road height. So here, these are the summary of results that we did. And so aside from testing the tensile strength and getting the modulus, we also got the mass in the different dimensions. In terms of our mass, we noticed that for our smaller nozzles, it was really, really light. So typically, the slicer predicted that it should have been 8 grams. And that's something we were quite confused and quite interested to study upon, where what happened to the 5 grams difference, or what caused this big difference. And again, this might be an issue in terms of like compressing the filament, which Professor Kazmer also talked in this talk to last week, and maybe again that filament slippage that we observed. Furthermore, this relation in MASH also translated into your tensile strength, where our basically weakest parts were also incurred in the smaller diameters. Similarly, it is important to note that once you increase that road height, again, we set it around below 80% of the nozzle diameter. So this was around 50% of the nozzle diameter. And you can see that huge decrease in terms of tensile strength. So around from 30, once you set it around 25%, you see that once you increase that, basically that layer height, you see almost an 18 megapascal decrease in tensile strength. Furthermore, you can see that there is some correlation between your tensile strength and your modulus decrease. So again, you also see the parts were very flimsy at this point, and basically you could, you know, if it would be very easily ripped apart if I had to give you these parts right now. So in terms of our different factors and how it affected our basically our parameters, and so varying the nozzles, we see that our larger nozzles actually produce 2.8 grams. Once you go to higher nozzles, your parts actually weigh 2.8 grams more than having it in the smaller nozzles. So you can see this again, the highest was around, I believe around almost 6 or 7 grams. Again, which is still a bit off from our theoretical 8 grams. In terms of printing from a higher height, you can see actually it's more, there's a bigger significance in printing a higher height where you actually have a big decrease in terms of your weight. And we have a reduction of 4.2 grams. It was statistically significant to say that your printing faster or slower does affect your part mass. However, again, this is very negligible in comparison to the 2.8 and 4.2 grams decrease, where printing slower or faster would have only changed your part mass around 0.086, or would have reduced it at 0.086 grams. Moving on to dimensions, again, something that we wanted to do was basically to have some sort of accuracy and precision. We wanted to have good and consistent parts. So something that we noticed was, again, printing with larger nozzles, just by nature, having larger nozzle would, of course, increase your, basically make wider parts, you know, because you're also depositing more of the material at that point. So again, that can be attributed to why we see this increase in our part width. Similarly, once you print at a higher height, again, you see basically it would be just drooping around. And so you see that beading effect that I presented in the second slide, where we'd have this poor adhesion. So that may account for the reduction in width. It's interesting to say that once you did this regression analysis, we had a really low R squared, and that it was actually not statistically significant to say that whether printing or our shear rates actually were not statistically significant in terms of affecting our part width. In terms of thickness, you see similar basically results where, again, printing larger nozzles, since you're depositing more material, you see a larger thickness in some sense, even though you have the same dimensions for the same parts. Furthermore, in terms of having larger road widths or basically printing it at a higher level, you do see this, again, it might have problems in adhesion because you're basically printing at a space where it would be just dropping and you basically not have that interlayer adhesion that we want for fused filament fabricated parts. Interestingly, unlike our width results, we saw that it was slightly statistically significant to see whether we print faster or slower in some sense. So that's something interesting to note down. Furthermore, in terms of our modulus or how stiff our parts were, you see that for larger nozzles, again, try to give it to you, and you can see that in the pictures themselves. Again, also from other literature that you typically have an increase in strength once you print in these larger nozzles because you're also depositing more material. Then the larger nozzles were around 1,176 megapascals stronger than, basically makes your part stiffer in some sense. Meanwhile, you would also, if you want it to be stiffer, you might want to again print it at a lower load height. However, again, there's this optimal range, and you can play around about it, but you also don't want to print it at a very low low load height because again, you might be just squishing that material, and again, it might just be compressing between the printer bed and your nozzle. So that's also something you don't want. In terms of how fast you print it or your shear rate, you do see some statistical significance, but again, it might be negligible where printing at a higher shear rate or printing faster would have only decreased your stiffness or your modulus by around 1.82 megapascals. In terms of tensile strength, it was quite amazing where, again, you see this huge decrease and huge increase and decrease in whether you print it at a large nozzle and smaller road height. Printing at the larger nozzles at the 0.4s and 0.8s, you do see this huge increase, as you can see in the graphs, that around 16 megapascals. So again, the parts are significantly more stiffer. However, again, you have this trade-off relationship between your resolution and part strength. Moreover, in terms of printing at a higher height, you see this large decrease in tensile strength. Again, this can be attributed to, again, poor interlayer adhesion. And basically, you'd see that beading effect that you don't really want. In terms of printing it faster or slower or shear rate, again, it is statistically significant to say that it does affect our tensile strength, but again, it's very minor to the whole grand scheme of things. So in terms of our relationship between part mass and ultimate tensile strength, something I learned from our basic structural product design and structural design is that typically, again, once you have more material, it's allowed to be, again, spread out. You have more, basically, it's able to carry more mass and more, in some sort of sense, be able to get more tensile strength. So you can see that once you have around 7 grams, you have the tensile strength around 38 megapascals, which was our highest value. And our lowest one was at, again, the lowest, basically the lightest ones, which were around less than 2 to 3 grams. And it incurred around basically a tensile strength of 1 megapascal. And so in comparison to literatural values or an injection molded part, according to NatureWorks, that polylactic acid grade that we used, once if you injection mold it, it would be around 60 megapascals. However, again, the highest one that we got was only 38 megapascals, and that was already at the 0.8 nozzle, which was quite interesting because we expected it to be stronger. Because once you also compare it with other literature, other data, some people, they only printed it using a 0.4 millimeter nozzle, also using PLA. They had around 50 megapascals. And you also see this in our modulus data, or how stiff our parts were, where it was significantly, again, not as stiff as other people's parts or what was thought or was theorized as an injection molded part from the material data sheet. So maybe just to wrap up, some key takeaways and best practices that we observed. One can attribute that aside from these part variations. This can be quite be due to, again, to that very bad filament we created. So that's a good indicator of whether your parts might perform as one would expect. Something that, again, that we also noticed and realized after all of this was that smaller nozzles will give you better resolution, but there is some trade-off between, again, your part strength, and it might be good to, again, there is some value in printing in larger nozzles in some sense, because I know that a lot of people only try one nozzle, or which is your 0.4, which comes with your typical desktop 3D printer. So there is some value in, again, going higher or lower depending on what you want. So our trends usually typically showed, again, larger nozzles, lower load heights, and lower apparent shear rates basically give you greater thickness, mass, tensile modulus, and basically tensile strength. Furthermore, these models were kind of validated with our Hoare regression values or coefficient of determinations, which were around 0.8 or higher. However, again, we might need more data on this, and it could have we could have compared different stuff as well later on, say. So again, conclusions, I can't stress enough, good and consistent filament is something that we really do need. However, don't worry if you have bad filament, there is still, it's not the end of the world. You can still tweak your parameters and maybe play around with larger nozzles to kind of normalize that bad filament. Because this, again, it's highly dependent on your quality. This will basically affect your quality and your part strength. And basically, in some sense, if you also print in with smaller nozzles, it can affect your part resolution. So some future work that we might have done, we could have done more regression analysis and studied the different interaction effects. We also printed only in the X-Y direction. I know there's a lot of interest once you print in the Z direction. We also could have compared to commercial polylactic acid filament or Ultimaker certified reduced filament, and further explore that relationship between why we had such a reduction in mass and like why it was so low. And maybe it was due to filament slippage. So again, I'd like to acknowledge my team, Aaron Mackert, Stephen Foster, Caleb Grolman, Vasili Lastochkin, of course, our advisor, Professor David Kazmer, for helping us with this research. And again, to UMass Lowell, to Society of Plastics Engineers for basically giving us the platform to share our research. Of course, to the plastics engineering community as a whole. Thank you very much.
Justin, thank you for a great presentation, and I also thank you for writing a paper for ANTEC. It's folks like you that make this society so great, so thank you. We do have a couple of questions. The first one, did you set the same print speed and flow multiplier for all nozzle sizes?
No, we did not. What we wanted to do was have the same volumetric output. So our print speeds were varied in order to have that same volumetric output, so we'd be able to compare it. Because if we were to just set it at the same print speed, you'd basically, if I'm not mistaken, it would be not a good, it would be basically not comparing apples to apples, or we'd be comparing like apples to oranges. That's why we ensure that we have the same volumetric output instead of having the same print speed.
I am not a failure expert, but when I looked at some of the breaks on those parts, it looked like there was two different failure mechanisms.
Yep. So our larger nozzles typically broke in a brittle manner, while the smaller nozzles, which had better resolution, it was more of like a fibrillar. I'm not sure again if this would be the right terms for it. Again, you see this like fibrillar. It would somehow have a larger strain per se.
Okay. Another question: is it required to program the printing head to make a narrower printing path to account for the smaller row width created by the smaller nozzles?
That's a good question. We haven't played around with that much, so I don't want to say that it is required, but I would believe so. It might. I would.
Okay. Professor Kazmer is putting in here a comment. He said that all had the same weld temperature. So I just put that in for the folks that you know, are involved with this kind of process. Another question was the filament consistency issue completed intentionally for the study, or were there issues with the extruder system?
Actually, this research, we initially started out with, again, with carbonate filament. However, we had a lot of problems with doing that. That's why we shifted to polylactic acid. And so in terms of whether we intentionally did have a lot of variations, I believe no, we never wanted to create bad filament. However, I think that was also a function of our single screw extruder in terms of like, I don't think we had a proper screw, or like it wasn't as consistent as we want. We're also using an older machine, so that affected it a lot. So again, we did not intentionally actually to make bad filament, but it ended up being bad filament. And we made the best out of it.
Thank you. One last question. It's the question is, did you decelerate and accelerate around corners? If so, did you consider the compressibility concept that Professor Kazmer discussed in his talk on April 6th?
We did not, to be honest, because once we were doing this, we didn't quite see that. Basically, we didn't talk of it enough, especially in our paper. I think we have expanded it more on that compressibility issue. Again, we didn't see that. We just basically set it as what it was. And so again, there's going to be a lot of, again, printer to printer variations, and we were not sure how the Ultimaker quite translated what we put in the Cura software and how it translated. So again, we did notice that it was somehow accelerating and decelerating, but we couldn't really quantify that effect. So
then as a follow-up question, do you think that this effect could account for any of the differences in the actual part weights?
Definitely, yes,
okay.
I completely agree. In terms of filament slippage and again compressing, yeah, I would definitely agree with that.
Well, that was the last question. Again, I thank you for a fantastic presentation.